recently defended his PhD on surface waves in the context of wave energy, and was here previously at OSU at the tsunami wave basin last summer when WEDZ was doing their small-scale testing, and Matthew did some testing on the side of their tests. So, you can take it off.
Cool. The project was involved with Industrial Research Limited, who are the guys who provide the sort of technical backing for the WEDZ project, and they're the ones who have developed the new device, which was just moored out of Newport. Very thankful for their support in this whole project. So for today, we're going to be looking at just a basic introduction to wave energy converters. Kind of was designed for a bit of a less specialist crowd, but we'll sort of run through that anyway. And in particular, looking at radiated wave theory. So for those who studied linear wave theory, they're taking a particular focus on circular waves. And also looking at how to measure circular waves. So there was an experimental component of the thesis. And examining the limitations, so with radiating waves, and what actually determines how good a radiator a body is, and sort of how that relates to wave energy. So to start out, just thought we'd start with a couple of the wave energy devices. Most of you will be familiar with the Laplace. To get a sense of scale, if you haven't already, it's about 3 meters in diameter, about 120 meters long. It's like standing next to a freight train when you see it on the dockside. It's a very, very impressive piece of equipment. And sort of one of the industry leaders at the moment. Last I heard they were doing pre-commercial testing, so the industry had bought a couple of these units and were testing them out in the Orkney Islands. And sort of haven't heard how that testing's going, but they're sort of fairly advanced in development. And this is actually the WEDZ device. This is their third prototype. It's what they call the quarter scale device. This was moored off outside of Akaroa, just outside of Christchurch. And yeah, that's some pretty big water there. That gives you a real sense of what's going on out in these oceans, and the sort of thing you can expect if you're designing a wave energy device. So they actually have a lovely video clip actually where they've, a couple of whales have pulled up alongside the device and are just having a bit of a look at it. And, it's quite impressive to see that they just kind of came up to it, looked at it, swam off. In terms of surface waves, I looked in particular at linear wave theory. And surface waves can occur at an interface between two bodies of fluid. So, I mean, the example that everybody knows is the ocean waves you see crashing on the beaches, and that's at the interface between a body of air and water. You can also get waves happening within a body of water where you've got, for instance, two layers of water with different salt content, and you can actually get what they call internal waves moving through, which we've sort of done a lot of studies up in Alaska about how these waves sort of eventuate and conspire, but they can transfer huge amounts of energy, and they don't necessarily need to be visible. One of the key things is that the depth effects, the properties of surface waves tend to be limited by depth. So if you're in shallow water, it changes how the particles move compared to deep water. There's a mathematical basis for all of this, and basically what people do is solve the Laplace equation in rectangular coordinates, and you end up with a velocity potential. For those who aren't particularly familiar with velocity potentials, you can actually break this up into separate components, which end up being relatively simple. So the first component on the end there is sort of a physical factor component. It's got your gravity and the speed of the wave and the amplitude and phasing. You've got what is effectively the depth component. So this is the drop-off of properties with depth. And the last component is a variation. So this is the harmonic with space and time. So you've got the x and the t term in there. Once you've got the velocity potential, you can use complex wave theory to go through and calculate a myriad of different properties, including the time average power for the wave, which is we'll have more use for that in a little bit. And you can go ahead and graph these waves and see what they look like. So this is a pretty simple plane wave. The little black arrows actually tell you the particle velocity direction and magnitude. So you can tell where the water's going. At the top of the wave, it's heading in the direction of propagation. At the bottom of the wave, in theory, it's coming back. Real waves are a little bit different from this, where the particles drift. But for a basis, for a starting point in the theory, it's proven pretty good. The key points of point absorber theory, so actually just popping back to those two devices we showed at the beginning, you had the Polaris, which is known as an attenuator. It's sort of quite long and should be pointing nose on to the incoming wave, whereas a point absorber is something which should be small, has a small horizontal extent compared to the incident wave wavelength. And there's a lot of theory built up around these point absorbers. There is an optimal absorption point, so there's a point where the device interacts with the wave that absorbs the most energy possible. So if you start to move in the wrong way, you start to not be as efficient. One of the other key points is that it's theoretically possible to absorb more power than is incident on the device. Now this may seem a bit counterintuitive in terms of engineering work, but the core of it comes from the fact that we're looking at a wave effect. So for instance, if you have a certain power per meter, the theory says that you can absorb up to 16 times your, or 16 meters of wavefront from a point absorber if you're working in heave. If you're working in a surge direction, you can double that. And then all it is a matter of, well, how big is your device, and then you can look at your performance. But we'll get a bit more into that and how it works. There's actually an analogy for that in radio waves. So when you look at radio antenna, they have the same effect where they're quite small and narrow frames, and they can actually absorb more energy than is incident on the device, on the antenna. And it's about the sort of wave effect and wave interaction that has led a lot of the people like phones to come up with this statement that a good absorber requires the wick to be a good radiator of waves. And I'll explain that in a bit more detail in a few more of these videos, see how that works. What I want to do is I want to start with a really simple classification of wave energy devices, and just classifying them in two categories. The first is dissipative and the second is conservative. So a dissipative device works by flow effects around the device, basically. So it's about friction, it's kind of pretty much what you're, it's about how it flows around, and there are a lot of losses in the system. A conservative device, on the other hand, takes out the energy from the waves purely on adding a destructive interference basis. So you add a radiated wave to a plane wave and you get energy out. This has been studied quite well in particular 2D, and I can explain how that works using this graph. So at the top of the chart there, you've got a regular plane wave rolling in from left to right. In the middle here you have what's known as a heave wave or a symmetric wave, and you'll see that as it goes off in either direction it's got exactly the same phase, but it's sending the wave out from the line of your wick. Yeah. And so the last type of wave you can have in the 2D case is a non-symmetric wave. And this would be generated by a wave energy converter sort of surging backwards and forwards in this direction. And the idea is you can add up all of these waves, and you'll notice on the bottom right hand side you've got no wave, and on the left hand side you have the incident wave rolling in. So in the 2D case, this is how you would try and cancel out your wave using a conservative system. However, when you start to look at it in 3D, it becomes a lot more complicated. In the 2D case there, the amplitudes of the wave continued on at the same height as you moved further off to infinity. However, when you radiate a wave in three dimensions, you have to account for the fact that the amplitude of the wave is going to decrease, like the waves when you sort of throw a pebble in water. They get smaller and smaller as they go out, as the energy gets distributed over a greater area. So one of the main questions asked is, what do the conservative wave interactions look like in 3D? And is there a linear wave theory that can be used to model these three-dimensional waves? And with that, how much power can you absorb based on these wave interactions? And are they the same as the hydrodynamic theory, which has been developed previously? So what it is focused on the solutions to the Laplace equation in cylindrical coordinates. Use cylindrical coordinates because I thought they could be most like circular heave waves, and as your coordinate system gets more and more complicated, the solutions for the Laplace equation get equally more complicated. You can solve the Laplace equation in what's known as elliptical cylindrical coordinates, which distorts the field instead of being a circular cylinder, so it becomes more elliptical. And the solution for that is what they know as called Matthew functions. But for the scope of this study, I've just limited it to the circular cylindrical coordinates. The solution down here looks like a bit of a mouthful, but just in the same way for the plane wave, you can break it up into set areas. So again, you've got the physical factors term on the left-hand side there. Again, just your gravity, the size of the amplitude of the wave, and the frequency. This term here is a new term. This is basically a spatial variation term, and so this controls whether you're a heave type wave or a surge type wave, and you can rotate non-symmetric waves using this term zeta on the end here, and I'll show you a bit more about that. Then you've got exactly the same depth term that you had in the plane wave case, and on the end here you have your spatial and temporal variation. The spatial variation ends up being what's known as Bessel functions, in particular the sum of two Bessel functions called the Hankel function, and this factor m here controls the order of it. I've got some representations to help show what that actually does. So this here is a circular wave. This here, the Bessel function has an order of 0, and you can see that the wave is completely symmetric. So, and as it sort of goes out with a greater and greater radius from your point of radiation, the wave gets smaller and smaller, as you would expect it for the whole, from the pebble in the pond example. And the next wave is the next higher Hankel order, which is the first order Hankel function. And this is like a device is sitting at the centre point and surging forwards, pushing a lump of water forwards, creating a void behind it, and then surging back, pushing the water backwards. So it's sort of moving backwards and forwards in that direction. Now, what you can do is you can, using that zeta term, which I talked about the rotation of, you can actually spin this around. So this line of no fluid motion